Alright everyone, so welcome back to week 5. That means we are now into the final third of the course. So what we're scheduled to do between today and tomorrow is to talk about plotting functions. So I think what I'm going to do is I'm just going to combine the two topics into one video, just for simplicity more than anything. So the first thing that we want to talk about before we can actually get into plotting functions is maximums and minimums. So what we'll say is that if we have some function f over an interval I, and we have some point c that's in our interval. If f of c is the biggest value that occurs on our interval I, then we'll say that f of c is an absolute maximum. So one thing that we could have with this is we don't necessarily have to have f of c occurring in only one place. It could occur in multiple places, totally fine. We'd still have an absolute maximum though. So for example, if you had a constant function, every value is the same, but you'll still have an absolute maximum. And in the reverse situation, if f of c is the smallest value that shows up on the interval I, we'd say that f of c is an absolute minimum. Now, we're not always guaranteed to have absolute maximums or minimums, but in certain particular cases we do. So in the case where you're dealing with a continuous function over a closed interval, you are guaranteed to have an absolute maximum or minimum, or absolute maximum and minimum. Okay, so first let's think about the function that is defined over the interval 0 to 1, that is defined to be 0 at x equals 1 and x everywhere else. Well, the first thing that we can see from this is that the smallest value the function will take on over the interval 0 to 1 is 0. We have that x equals 0 is going to be, f of 0 is 0, and f of 1 is also defined to be 0. So we don't have any negative numbers, we have nothing smaller, so 0 is going to be the absolute minimum, and it will occur at x equals 0 and x equals 1. At the same time, there is no absolute maximum. And the reason for that is because there is no biggest value that the function takes on over this interval 0 to 1. If you proposed any value, like 0.99, I could always get a slightly bigger value by moving a little bit closer to 1. So if you propose that 0.99 is the absolute maximum, I can move over to 0.999, get something bigger. So there's no absolute maximum here. Now, let's say that we went and we looked at the function x squared over the entire real line. If we did that, we would have that the absolute minimum is 0 because the function is 0 at x equals 0, and there are no smaller values. But there's clearly no absolute maximum here because the function goes off to infinity. If we restrict things down and we look at the closed interval 0 to 2, what we'd see is that we have an absolute minimum still at x equals 0, but we now have an absolute maximum at 4, and that's occurring at x equals 2. And this would make sense because we have a continuous function over a closed interval. Now, if we went and opened up the left side of the interval, so we went with an open interval from 0 to 2, we wouldn't have that absolute minimum at 0 anymore, for kind of the same reason as before. And then we could open up the right side of the interval, and we'd also have we would have neither an absolute maximum nor minimum. Okay, so then we could go and look at this W kind of shaped curve, and what we'd see here is that we have these absolute minimums that are occurring at about minus 1.5-ish and plus 1.5-ish, and values are a bit under -2. But we wouldn't have an absolute maximum because we've said that the intervals are open on the left and the right. But there's also something going on around x equals 0. And what we'd see there is if we'd taken a smaller interval, so say we'd taken the interval -1 to 1, then we would have had an absolute maximum at x equals 0, but as it's currently written, we have no absolute maximum here. So this is something that we're going to come back to in a little bit. Okay, so one important part when dealing with maximums is what are called critical points. So critical points are going to be any place where the derivative is 0 or the derivative does not exist. And usually the derivative being 0 is the one everyone remembers, but the derivative not existing is also very important. And if you forget that, you're going to miss critical points, which can lead to some problems. So the first thing that we're going to do is we're going to go and find all of the critical points of x squared times the natural logarithm of x. Okay, so the first thing that we want to do is we want to look at where our function is actually defined, because if our function isn't actually defined, anything that follows isn't really of interest. So first place is where the derivative exists, to at least look for places that could be critical points. And what we see is that the natural logarithm is undefined for 0 and negatives, so our function is only defined over the positive numbers. Okay, so we'll write our function as g times h, and then use our product rule. So we'll get a derivative of x times 2 natural logarithm of x plus 1. And we first want to ask where our derivative does not exist. And from this we can see the derivative won't exist at 0 or negatives because of that natural logarithm, but the function's not actually defined there, so those points aren't going to be of interest to us. So we're just looking for where the derivative is going to be 0. So we've got a derivative which is two functions multiplied together, and if the derivative is going to be 0, it's going to occur at the places where the individual factors are 0. Well, the first factor we have is just x, and that's clearly going to be 0 at 0, but we've already said that's not of interest because the function's not defined there, and also the derivative isn't defined there. So the only place we're going to get for a critical point is anywhere where 2 natural logarithm of x plus 1 is 0. And from that, we could easily solve that to get x equals e to the minus 1/2. So x equals e to the minus 1/2 is going to be the only critical point for this function. Okay, so how do we go about finding absolute maximums and minimums? So what we'll do is we'll take some closed interval a to b, and we'll first go and find all of the critical points over that interval. So all of the places where the function is defined, but the derivative is either 0 or doesn't exist. Then for each of these critical points, we'll put them back into the original function, not the derivative, the original function. And we'll also go and evaluate the two endpoints as well. And then the third thing that we'll do is we'll take the largest value that appears in step 2 and also the smallest value that appears in step 2. And the biggest value that we get will be the absolute maximum, the smallest value we get will be the absolute minimum. So we'll go and do a couple of examples. We'll first go and find the absolute maximum and minimum for x cubed minus 3x squared minus 9x plus 2 over the closed interval minus 2 to 2. Okay, so the first thing that we're going to want to do is go and find our derivative, and because we're dealing with a polynomial, well, we know that our derivative is going to exist, and our derivative is going to be defined everywhere. Okay, so then the next thing that we're going to want to do is factor everything. So usually when doing these, factoring is really, really convenient, and if you don't factor, you're going to make things harder on yourself. Okay, so we'll factor our derivative as 3 times x minus 3 times x plus 1. And from this, we can easily see our derivative is 0 at x equals 3 and x equals minus 1. But because we're looking over the interval minus 2 to 2, the critical point of x equals 3 is not going to be relevant, so we're just going to casually discard it. Okay, so we just need to look at 3 values. We need to look at f of minus 2, which is 0, f of minus 1, which is 7, and f of 2, which is minus 20. And what we see here is that the biggest value that's showing up is 7, so that'll be our absolute maximum, occurring at x equals minus 1. And the smallest value that we have is minus 20, and that's occurring at x equals 2, so that'll be our absolute minimum. Okay, so the next one. So we want to find the absolute maximum and minimum for 3x to the 2/3 minus 2x over the interval minus 1 to 1. Okay, so we'll first go and find our derivative and factor it as 2 times 1 minus x to the 1/3, all divided by x to the 1/3. So what we see here is that we have that g prime of 1 is 0, and that's great, but we already had to look at x equals 1 because that's an endpoint. And then we have that the derivative won't exist at 0, but the function is defined at 0. So we do indeed need to consider what's going on at 0. Okay, so we have our critical point of 0 and our endpoints minus 1 and 1. And when we put those values all back in the original function, we get that the biggest value showing up is 5, and that's occurring at x equals minus 1. Smallest value is 0, and that's occurring at x equals 0. So if we hadn't considered the place where the derivative was 0, the derivative didn't exist, we would have missed the critical point. And in fact, we would have missed our absolute minimum. Another, I guess, a simple way that you could, a simple illustration to see why the absolute maximum and minimum, you need to go and find places where the derivative doesn't exist, is you could think about the McDonald's arches. So the McDonald's arches in the middle, they have a cusp, so a sharp point. The derivative is negative to the left of the middle and positive just to the right of the middle, and that's what's forming that cusp there. And what you would see is that if you did drew the McDonald's arches and maybe you drop the middle part down a bit, that'll give you a minimum. So the places where the derivative doesn't exist are also important. Okay, so then we can also ask where a function is increasing and decreasing, and that'll also be useful when we're going to plot functions. So a function is increasing if as you move to the right, the value of the function increases, and it's decreasing if as you move to the right, the value of the function gets smaller. And that's nice, but maybe somewhat annoying to actually try and find. But what's convenient is that we can also say that a function is increasing wherever the derivative is positive and decreasing wherever the derivative is negative. So we'll go back to x cubed minus 3x squared minus 9x plus 2 and ask where that function is increasing and decreasing. So again, we'll factor our derivative as 3x minus 3 times x plus 1. And then we're going to make a table. So I'll try and explain everything that's going on here. So what we have along this row is we've split the real number line up based on where the derivative is 0. So the derivative we could see is 0 at minus 1 and 3. So we're going to split the real number line up into these sections. So we'll look at everything to the left of minus 1, everything in between minus 1 and 3, and everything bigger than 3. And I have just here representatives. So what I'm just doing there is using representatives for each of these intervals. And on the column, I have every factor in f prime that could change sign on us. So we have x minus 3 and x plus 1, because we're going to really only concern ourselves with signs. Okay, so when we're looking for values that are to the left of minus 1, such as minus 2, if we take minus 2 and put it into x minus 3, we'll get sign negative. If we put minus 2 into x plus 1, we'll also get sign negative. When we multiply those two together, we have a negative times a negative, so f prime is positive, which tells us that f is increasing. When we look between minus 1 and 3, we could take 0, put it into x minus 3, and get sign negative. But when we put 0 into x plus 1, we'll get sign positive, which tells us that our derivative, when we multiply the factors together, will be negative, so the function is decreasing. And similarly, we could find that for x bigger than 3, the derivative is going to be positive, so the function is increasing. So what it'll tell us is that our function is going to be increasing to the left of minus 1, to the right of 3, and decreasing in between minus 1 and 3. Okay, so let's come back to this W curve. So we'd said that if we went, instead of looking over the interval minus 2.5 to 2.5, we just looked over, say, minus 1 to 1, we'd get that x equals 0 would give us an absolute maximum. But when we look over the interval minus 2.5 to 2.5, it's not an absolute maximum anymore. So we can talk about different kinds of maximums and minimums as well. So we'll talk about what are called local maximums and minimums. So basically what local maximum and minimum says is that you're getting a maximum for a subinterval, which is kind of what I'd alluded to before. So suppose that you have some grand interval I, and if you take some smaller interval I prime, then your f of c is the maximum on this smaller interval I prime. Then that's going to tell you have a local maximum, and if f of c is the smallest value, you'd have a local minimum. Okay, so in the event that you have a local maximum or minimum, and also the derivative is existing at that point, then the derivative is going to be 0. So what does this tell us? Well, it tells us that if we want to go and look for local maximums and minimums, we should start by looking for places where the derivative is 0 or doesn't exist. Okay, and then we have what's called a first derivative test. So what we'd like to do is be able to classify critical points based on whether or not they are local maximums, local minimums, or possibly neither. So if what you have is the derivative is positive to the left of some critical point C and then negative to the right, you're going to have a local maximum there. So I'll explain things at the end. So the second possibility is that your derivative is negative to the left of your critical point and then positive to the right, and in which case you have a local minimum. And the last case is that your derivative is positive on both sides of your critical point or negative on both sides of your critical point. In that case, you have neither a maximum nor a minimum. Okay, so let's just try and illustrate these three possibilities. So case 1. You could think about it as you're going up to the top of a roller coaster. So when you go up to the top of the roller coaster, you start increasing, you hit the top, and then you start going down, so you start decreasing. Well, clearly when you're going up and then you start going down, you've hit a maximum. But then once you start going down, you hit the bottom of the roller coaster and then you start going back up, that's going to be a minimum. Okay, and then the third possibility I'm going to illustrate nicely with water slides. Okay, so if I remember right, I think this is the world's largest indoor water park, and it's in the mall in Edmonton, Alberta. So there's this purple water slide over here, and the way it works is that you start up here, you go down a bit, you plateau, then you start going down again, you plateau, and then you finally go down into the finishing pool. And what we can see here is that in this area where you're plateauing, you're decreasing, you hit this kind of plateau area, so your derivative is going to be 0 there, and then you keep going down again. So what we'd have here is, when we're in this plateau, we're at neither a maximum nor a minimum. Also, if you ever happen to be in Alberta, I do strongly recommend going there. It's a lot of fun. It's a good way to spend an afternoon. Okay, so then back to this. So let's go and find local and also absolute maximums and minimums for this function x minus x to the 2/3 over the interval -1 to 2. Okay, so first we'll want to go and find our derivative. So our derivative after factoring, we'll get 3 times x to the 1/3 minus 2 over 3x to the 1/3. From this we can clearly see the derivative does not exist at 0. So that'll give us one critical point. And then if we're looking for where the derivative is 0, we'll set the numerator equal to 0. So we'll say that 3x to the 1/3 minus 2 is 0. And after solving that, we'll get x is 8/27. So we'll have two critical points. One is at 0, the other is at 8/27, and both are inside the intervals in question. Okay, so to find our absolute maximum and minimum, we'll put our endpoints of -1 and 2 back into the original function, and also the critical points of 0 and 8/27. When we do this, we see that the smallest value that we're going to get is -2, and that's occurring at -1. And the biggest value that we're getting is about 0.41, and that's occurring at x equals 2. Okay, so that gives us our absolute maximum and minimum, but we also want to come up with the local maximum and minimum. So we'll put all of the factors in f prime that can possibly change sign on us into our table. So we have our numerator, which can change sign on us, and also the denominator. And then along the top, we'll put our critical points, so all of the places where these factors could change signs. So when we look at x values that are to the left of 0, something like -1, if you put -1 into here for x, you'll get something negative. Put -1 into your denominator, you also get something negative. Do remember that odd roots of negative numbers are perfectly well defined. So -1, so the cube root of -1 is -1. Because if you take -1 and multiply it by itself 3 times, you get -1. Okay, so then our derivative will be positive for negative numbers, so our function is increasing for negative numbers. In between 0 and 8/27, the numerator will be negative while the denominator is positive, so the derivative will be negative and the function is decreasing there. And then for x values to the right of 8/27, the derivative will be positive, so the function is increasing. Okay, so we've talked so far about the first derivative, and we can now start talking about things we can pick out of the second derivative. So we'll say that a function is concave up if our function is differentiable and f prime is increasing. So in other words, the function is concave up if the second derivative is positive. And we'll say the function is concave down if the function is differentiable and f prime is decreasing. So the function is concave down if the second derivative is negative. Simple illustrations of these are a smiley face is concave up, so it's opening upwards, and a frowny face is concave down because the function is opening downwards. And then in the same way that we had critical points that talked about the first derivative, we have inflection points that tell us about what's going on with the second derivative. So a place where the second derivative will change sign, so positive on one side, negative on the other, those will be inflection points. Okay, so we had a first derivative test and we could also have a second derivative test. So let's say that we have a critical point, f prime of c is equal to 0, and our second derivative is negative. So in other words, our function is opening downwards. That will tell us that c is going to be a local maximum. And this is maybe counterintuitive because you would think that maybe just if you were guessing that if f double prime was positive, c would be a local maximum. No. If f double prime is negative, then c is going to be a maximum. So let's go back to the roller coaster. When you're going up to the top of the roller coaster and then going down, you've hit a maximum. And if you look at the roller coaster tracks from the sides, you would see that the tracks are opening downwards. And that's going to tell you that the second derivative is negative. Conversely, if the second derivative is positive, you're going to have a local minimum, same kind of idea. If you look at the tracks from the side and you see that, you would see that the tracks are opening upwards, so you'd have a local minimum there. And if you have neither, if your second derivative is 0, you're going to have no conclusion. So it could be the case that you've got a local maximum or local minimum or neither. All three cases are possible. So if I go back to the water slide here, what you would have, if you were to plot this, is that your second derivative would be 0 at this point, where the water slide is plateauing. And as we said, we have neither a local maximum or minimum. Also, while I've got this up, I'll also just shill a little bit more for them all. This slide, you go into it and you spin around kind of like when you would drop a penny into one of those. I think they have one at the DQ in Laramie. You drop a penny and it kind of whirls around the little thing before falling into the bottom. That's what that slide is. This one, you have a little bit of a board that you go down a ramp and you try to stay on it when you hit the pool. I want to say this is the world's largest indoor wave pool, but I'm not sure offhand. And from behind where the camera is taken is a massive, it's a massive bungee jump. So there's a bungee jump, and if you hit it just right, you can get just into the wave pool. Okay, so we'll do two examples that'll wrap up what we've said about increasing, decreasing, and concavity. So we'll take two examples and work with them. So we'll first take the polynomial 2 plus 3x squared minus x cubed, and we'll find the critical points, places where we're increasing and decreasing, places where we're concave up and down, our inflection points, and our local max and mins. Okay, so as before, we want to find our first and now second derivative, and we want to factor both. So we'll find the first derivative as 3x times 2 minus x, and our second derivative is 6 times 1 minus x. Clearly we're dealing with polynomials, so everything exists everywhere. So from f prime, we see that f prime is going to be 0 at x equals 0 and x equals 2, so we'll split the real number line up for all of the x values to the left of 0, x values in between 0 and 2, and x values to the right of 2. And the factors that can change sign on us are 3x and 2 minus x. So when we're looking at values to the left of 0, such as minus 1, 3x will be negative, 2 minus x will be positive, so that tells us the derivative will be negative, function is decreasing. In between 0 and 2, so something like 1, 3x will be positive, 2 minus x will be positive, so our function will be increasing there, and then lastly we'd get that the function will be decreasing to the right of 2. Okay, and then when we're looking at our second derivative, the only factor that we have here that could change sign on us is 1 minus x, so that's going to be 0 at x equals 1. So we just need to split things up to get the values that are to the left of 1 and also to the right of 1. Well, when you have a value to the left of 1, such as 0, 1 minus x will be positive, f double prime is positive, and f is going to be concave up. And values to the right of 1, such as 2, 1 minus x is negative, f double prime is negative, so f is concave down. And then what we said we wanted to do was go and classify our critical points based on a derivative test. So we'll do both and we'll see that they give us the same result. So when we look at 0, we see that we're going down to the left, we hit 0 and then we start going up. So as we said with the roller coaster analogy, we've hit a minimum there. And for x equals 2, we're going up, we hit 2 and then we start going down, so we're going to have a local maximum there. And if we use our second derivative test, we'll see we get the same thing. So we said that at x equals 0, our function is concave up. Well, from our second derivative test, it tells us we have a local minimum. And at x equals 2, we see the function is concave down, so we've got a local maximum there. And then the other thing we could do just for completeness, because we said we wanted to find inflection points, we see that the sign of the second derivative is changing at x equals 1, so we've got an inflection point at x equals 1. Okay, so then the other thing that we wanted to do is we wanted to finish this off by looking at the example g is x divided by 1 plus x squared. And I've gone and done the quotient rule for both of these to go and also factored them to go and get the derivatives. So what we see is that g prime is 1 minus x times 1 plus x, all divided by 1 plus x squared. So we can note that the first derivative and also the second derivative are going to exist everywhere because it's not possible for the denominators to be 0 in either of these cases. We have 1 plus something squared, so we'll get 1 plus something that's always at least 0, so it's not possible for these denominators to be 0. Okay, so the first thing that we can see is that our first derivative will be 0 at x equals 1 and minus 1, so we'll go and split the real number line up to get values to the left of 1, to the left of minus 1, values in between minus 1 and 1, and then values to the right of 1. And when we do that, we see that 1 plus x will be negative to the left of minus 1, 1 minus x will be positive, so our derivative will be negative there, the function is decreasing. in between -1 and 1, so such as x equals 0. Both of the factors will be positive, so our function will be increasing. And then when we move to the right of 1, we see that our function will be decreasing over there. So we could also go and categorize our critical points based on our first derivative test. And as before, we see that we'll get a local minimum at -1 and we get a local maximum at +1. When we go and we look at our second derivative, there are 3 places where the second derivative will be 0. So we'll see that we'll have the second derivative is 0 at x equals 0, x equals plus square root of 3, and also x equals minus square root of 3. So we need to split up the real number line to give us x values to the left of minus the square root of 3, x values in between minus square root of 3 and 0, x values in between 0 and square root of 3, and then x values to the right of the square root of 3. And the factors that we have here that can change sign on us are x minus square root of 3, and x plus square root of 3. Again, this denominator will always be positive because we have 1 plus something that's always at least 0. So because it's always positive, we don't need to worry about it. You could include it if you want, but it would just always be positive. So what we see when we do this is that we'll get that our second derivative will be negative for x values to the left of minus the square root of 3, positive for x values in between minus square root of 3 and 0, negative for x values in between 0 and square root of 3, and then positive for x values bigger than the square root of 3. And if we wanted, we could also use this to give us, to characterize our critical points. So we'd have that at -1, the second derivative is positive, and from our second derivative test that would tell us that -1 is a local minimum, which concurs with what we just said. And at x equals 1, the function is going to be concave down, so we'd get a local maximum at x equals 1, as we just said. And then what we see is that the sign of the second derivative is changing at minus square root of 3, 0, and also square root of 3. So all 3 of these points are also going to be inflection points. Okay, so that takes care of the first thing that we want to talk about before we get into plotting functions. And now we can use all of these things to actually start talking about how we're going to plot some functions. Okay, so the main idea is how could we plot a function like this without resorting to technology? Well, so we want to go and look at 6 different things. So we want to look at symmetry, which is something that we haven't talked about yet, intercepts, which we also haven't really talked about yet, asymptotes, which we've mostly covered, and then the 3 things that we just talked about. So critical and inflection points, where a function is increasing, decreasing, concave up, concave down. So a function is said to have even symmetry if it satisfies the relation that f of x is f of minus x. And a function has odd symmetry if f of x is minus f of minus x. And the names for these symmetries are not showing up by accident. So what I have here is a plot of sine of x, and sine of x has odd symmetry. And the reason why sine is going to have odd symmetry is because if you did a polynomial expansion for sine of x, something that we haven't really talked about but you focus much more on in Calc 2, what you see is that you could write sine of x out as x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial, and so on. So you'd sum up an infinite number of these terms. But what we see here is that sine only has odd powers of x showing up, and that's where the name odd and also even is coming from. So if you only have odd powers of x showing up, you're going to have odd symmetry. And likewise, if you have only even powers of x showing up, you're only going to have even symmetry. Pictorially, what the odd symmetry is saying is that if we pick some point over here like 2, and we look at the f of x value, when we go and look at minus 2, we'll get the negative f value. And that's what we'd see from sine of x. If we go and we look at cosine, we'd see that the polynomial expansion has only even powers of x. A constant like 1 is x to the 0. 0 is an even number, so we have only even powers of x showing up for cosine. And even symmetry is pretty easy because it just means that you can mirror things across the x-axis. So when you go to some place on the positive side, you're at the same value when you're on the negative side. So 1 and minus 1, they have the same value. And you could do that for all of the values. Everything nicely mirrors across the x-axis. If you have a mixture of even and odd powers of x, so something like sine plus cosine, you'll have neither even nor odd symmetry. So like this example, neither even nor odd symmetry, because we have this mixture of even and odd powers of x. Okay, so then let's remember what we said about asymptotes a while ago. So we have something like 1 over x squared. Around x equals 0, the function is going off to infinity, and we said those are vertical asymptotes. When we looked at limits as we went to plus or also minus infinity, if the function went to a number, we said that we had a horizontal asymptote. So we had a line y equals something or other. But there's also what's called a slant asymptote. So the idea with a slant asymptote is kind of similar to that of a horizontal asymptote. So the horizontal asymptote, what we said was that the function was going towards a number, or in other words, the function was approaching a horizontal line. Now what we're going to have with a slant asymptote is that our function is approaching just a generic line, so a y equals ax plus b kind of line. So the idea with that is just if you put forward some line y equals ax plus b, subtract it off from your function, and take the limit of that difference as x goes off to plus and also minus infinity. If that limit goes to 0, then you have a slant asymptote. Right, so let's take the function x squared plus 1 over x, and I've plotted it from minus 5 to 5. What we see is that x goes to plus or minus infinity. It's getting really, really close to this dashed line, and that's the idea of a slant asymptote. And if we wanted, we could propose that the line is just the line y equals x, because if we take this function x squared plus 1 all divided by x, and we subtract away an x, that difference is going to be 1 over x, and as x goes to plus and minus infinity, that difference goes to 0. So you could find a slant asymptote like that. Okay, so here's the main steps that we want to carry out when we're trying to sketch a function. So we're going to pick off various qualities from the function, its derivative, and its second derivative. So we'll go and find where our function is defined. Then we'll pick off any asymptotes from the function, identify any symmetry and also intercepts, so places where the function crosses the x-axis, and also the x equals 0 point is usually the other one. From the first derivative, we'll do what we just did. So we'll find critical points, local max and mins, and also where the function is increasing, decreasing. And then for the second derivative, we'll find inflection points and where the second derivative is increasing and decreasing. Okay, so 2 examples for this. So we'll sketch x squared plus 2x plus 4 all over 2x, and then we'll do x squared minus 1 over x squared minus 4. Okay, so first, for x squared plus 2x plus 4 all over 2x, we could see that our function is going to be defined for every x value that's not 2, because there the denominator is 0, the numerator isn't. Okay, so then we could go and rewrite our function as x over 2 plus 1 plus 2 over x, and what we'd see is that if we subtract off the line x over 2 plus 1 from f of x, that difference will go to 0 because of this 2 over x as x goes to plus and minus infinity. So it'll tell us that we have a slant asymptote of x over 2 plus 1. And then as we said, we have this vertical asymptote at x equals 0, and our intercepts are actually not going to happen. So there's not going to be any place where this function evaluates to 0. And also the x equals 0 point's not defined. Okay, so this red dashed line is just going to be the line x over 2 plus 1. And what we've said is that as the function gets close to, goes to plus and also minus infinity, it's going to get really close to this dashed line. Okay, so then, well, what we said is that our limits as x goes to 0 from the right, 0 from the left, using what we know about limits and infinity from the first week, we'll get that the right side limit at 0 is going to be plus infinity, the left side limit at 0 is going to be minus infinity. So we can go and add that into our function, or add that into our sketch. So as we go towards x equals 0 from the right, we see the function's heading off to plus infinity. As we go at 0 from the left, we see it's going down to minus infinity. Okay, so then we'll go and find our first and second derivatives and factor them. We'll see that our first derivative is going to be x minus 2 times x plus 2 all over 2x squared, and our second derivative is 4 over x cubed. So clearly our critical points are going to be plus and minus 2. The derivative is not defined at x equals 0, but we're not really concerned with that because the function is not defined there either. Okay, so the factors that can change sign on us are just the x minus 2 and the x plus 2, because that denominator is always going to be positive because it's a 2x squared. So we'll go and split things up based on x values to the left of minus 2, x values in between minus 2 and 2, and then x values to the right of 2. When we do that, we see that we're going to be increasing as we approach minus 2 from the left. We hit minus 2 and then we start decreasing. So we're going to get a local maximum at minus 2, and then we decrease until we hit 2, and then we start increasing, so we'll get a local minimum at x equals 2 as well. When we go and we look at our second derivative, well, we have 4 over x cubed. So what we see is that for the negative numbers, our second derivative will be negative, so concave down for the negatives, and then concave up for the positives. And then we can put everything together and we can get this plot. So what we'd see, it's maybe a little bit hard to identify from this exactly where the local maximum and minimum are occurring, but trust me when I say that they are occurring at x equals plus and minus 2. And what we see is that as the function gets closer and closer to plus and minus infinity, we're getting closer and closer to this red dashed line. We'd said that our function was increasing until we hit minus 2, and then we start decreasing. So we've got this local maximum here at minus 2. Our function is opening downwards on all of the negatives, and that's what we wanted. And our function is opening upwards over here on the positives, local minimum at x equals 2. Okay, so then we'll go and we'll do the second example. So we'll do x squared minus 1 over x squared minus 4. And what we can see is that our function is defined everywhere except for x equals plus and minus 2. Our function is going to have even symmetry because we've got an even function divided into an even function. So you could think about this as it's going to work like subtraction. You subtract an even number from an even number, you get an even number. The vertical asymptotes that we'll get will be at plus and minus 2 because that's where the function is going to go off to infinity. And if we were to take our limits going to plus and also minus infinity from what we said back during the first week, we'll compare the ratio of the leading terms, get 1 over 1. So we'll have a horizontal asymptote of y equals 1. And what we could also see is that we have intercepts at 0 and a quarter, 1, 0, and the point minus 1, 0. So we can put all of this information out there. So we have these 3 black dots representing our intercepts, and then we have these these dashed lines telling us where we have asymptotes. So we have vertical asymptote at minus 2 and plus 2, and then we have this horizontal asymptote at y equals 1. Okay, so around our vertical asymptote, we can go and take our one-sided limits. We'll get that the right side limit at 2 is plus infinity, the left side limit at 2 is minus infinity, the right side limit at minus 2 is minus infinity, and the left side limit at minus 2 is plus infinity. So we'll add that information into our plot. So we get these limits going down to minus infinity over here, and the limits going off to plus infinity to the right of 2 and to the left of minus 2. Again, this also makes sense because we said we have even symmetry, so everything should nicely mirror across the x-axis. Okay, so as before, I'll just go and put in the derivatives. If you wanted to verify these with the quotient rule and such, you could definitely do it, but I'm just going to skip over how we got these derivatives. So, TAMO, the best acronym in math, then a miracle occurred. So then a miracle occurred and we got these 2 derivatives. Okay, so what we have here is our denominator is always going to be either 0 or positive. 0 at places where the function is not defined. So 0 at plus and minus 2, but outside of those places it's positive. So we only really need to concern ourselves with minus 6x. That's the only thing here that could change sign. Clearly that's 0 at x equals 0. So what this says is that for negative numbers, our function is increasing. For positive numbers, our function is decreasing. Okay, and then we'll come and we'll look at our second derivative. So we see that the numerator here is always going to be positive because it's 3x squared plus 4. So we have something that's at least 0 plus 4, that's always positive, but the two things that we have in the denominator could flip signs on us, because an x minus 2 cubed, we can get negatives and positives out of that. So the places where our second derivative could switch signs on us are going to be at minus 2 and plus 2. So we just need to look at the signs of what's going on there. We'll split things up to get x values to the left of minus 2, x values in between minus 2 and 2, and then x values to the right of 2. And when we do that, we see the function is going to be concave up to the left of minus 2 and to the right of plus 2, and concave down in between minus 2 and 2. Now we'd said that the only critical point that we have is x equals 0, and from this, our function is going to be concave down at x equals 0, so we'll get a local maximum out of x equals 0, and that's our only critical point. Okay, so then when we put everything together, we get a plot that looks like this. Our function is concave up to the left of minus 2, concave up to the right of 2, and concave down in between minus 2 and 2. Our function is increasing for all of the negatives. Weird things can happen around where you have this vertical asymptote where the function is not defined, but it's increasing at all the other places, except at x equals minus 2 itself, because the function goes off to infinity there. Weird stuff happens there. And then over on the positives, decreasing everywhere except again at x equals 2, because the whole thing with infinity kind of messes up everything. Okay, so that goes and tells us how we're going to want to plot functions. So there will be a worksheet for you to work on in WoW courses, and I will see you all the next video, which will be for Wednesday.